have initiated the recording, and I also need to share the slides. So, yes, so my slides should also be visible now. Okay, so hello everyone, welcome once again to the second weekly problem session for the NPTEL course titled Physics of Nanoscale Devices. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, Indian Institute of Technology, Roorkee. So let us directly jump into today's session. So the topics that we shall be looking at are the following. So we shall spend like the first 15 to 20 minutes doing a small recap of week one, where we will directly solve a problem and try to revise all the concepts that were discussed in the first session. The video of that session along with the slides should all be available to you by now. Um, Let me know if you have any issues in that matter too. And after that, we shall be talking about the Kronig-Penney model, which is kind of where we left off last week's session. And through the Kronig-Penney model, we shall discuss the notion of electronic band structure of solids. And then we will come over to the idea of effective mass, and we shall approach the topic of the density of states. We shall not be spending too much time here because, as you might have seen in the lectures, the density of states discussion is just initiated in this part of like this week of the course. So the central discussion on density of states will be mostly in week 3. So next week we shall be diving into more details of that topic. So this is the recap. So most of week 1 session was spent on discussing solutions to the Schrodinger equation. So essentially, when we are looking at solutions to the Schrodinger equation, we are considering this equation here. So since this is 1D only, I will write the equation as minus h bar squared upon 2m d squared upon dx squared psi of x plus v of x psi of x equals e times psi of x. Yeah, so okay, I should actually add one more line here for bound states. Has the font gone up a size? Seems to be the case. Yeah, indeed it has. So this is yeah. Yes. Now it's right. So the potential that we are considering today is this potential. So this is known as the delta potential, or more specifically the Dirac delta potential. So this problem serves two purposes. The first being, of course, it is an example of how to solve the Schrodinger equation for certain special types of potentials. And second, this is also an introduction to the idea of the Dirac delta function, which will have some applications as we go through this course. So this function will appear multiple times in the duration of this course. So again, anybody who's studied any signals and systems or linear time invariant systems, any like graduate level analysis course should be familiar with what the delta function is. Nonetheless, I will write the definition. So delta of x again has a piecewise definition. So it is equal to infinity if x is equal to 0, and 0 if x is not equal to 0. So essentially, if I were to draw my xy axis like this, x and f of x, then the Dirac delta function will look something like, slightly thinner, something like this. So it's going to be completely flat for every value. Okay, yeah, this is too. Let me change the color to something more contrasting. Green, maybe. Yes. So everywhere this function is going to be 0 with the exception of, in fact, I should have inverted the colors. Doesn't matter. Except for, oh, dots. Except for 0 where this function will diverge just at one point to infinity. So this is kind of how the function will look. So it goes to infinity and it is 0 on both sides of the origin. And another important property of the Dirac delta function is the following. So, yeah. So if I were to perform the integral a to b of delta x dx, then this integral is also, it also has a piecewise definition. Before that, let me, yeah, I can do this. Really? Oh, come on. Yes. My axis is not getting selected. Yes. Let me move this to here. Yes. So this integral that we have here, yeah. So this integral from a to b of the Dirac delta function, again may have two values. It is equal to 1 if 0 belongs to this interval. Should technically be an open interval. Yes. And it is 0 otherwise. What does this mean? If I'm integrating it between 2 points, as long as the point where the Dirac delta function goes to infinity is within the limits of integration, then the integral will give me value 1. Otherwise, the integral will give me value 0. So these are the properties of the Dirac delta function. Now, using this, let us see how we can solve the Schrodinger equation. So, Schrodinger equation is going to be can be written as such for this problem. H bar squared upon 2m d squared by dx squared psi of x. Remember, this is minus v naught times delta x, where v naught is a constant. It is more precisely, it is a positive constant. Okay, so I'm considering a case where the potential, so if delta x goes to plus infinity, then minus delta x is going to go to minus infinity. And yeah, the next property I will like illustrate as I'm working it out. So minus v naught delta x psi of x is equal to e times psi of x. Yeah, So this is the equation. Now, how do we go about solving this? Because, I mean, there isn't any, like if this were a constant, we know how to solve it. If this were zero, we know how to solve it. We have not looked at any special techniques for solving this thus far. So what, but I know one thing. I know the property of the Dirac delta functions. So essentially what I'm going to do is first, I will integrate just 1 second. Let me put my phone on silent. Yes. So yeah, as I was saying, so first what we shall do is integrate both sides of this equation from, let us say, 2 points minus epsilon to epsilon. Okay, so minus h squared by 2n integral minus epsilon to epsilon d squared upon dx squared psi of x dx minus v naught is a constant, so I can keep it outside of my integral, minus epsilon to epsilon 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 to epsilon uh, delta of x psi of x dx, and yeah, is equal to e times, again e is taken to be a constant, so this is minus epsilon to epsilon psi of x dx. So now we come to the second property of the Dirac delta function, which is this. Again, most of you may be knowing this, but just for the sake of reference and completeness, I'm writing it here. So if I have, again, a to b delta x times any function f of x dx, then that integral also has two possible values. Firstly, it will be f of 0 if 0 belongs to this interval a comma b, 0 otherwise. So we know if we are integrating from minus epsilon to epsilon, then 0 definitely lies in the middle. So we know how to integrate this. Now this particular integral here, this is the second derivative of my wave function. So if I were to integrate the second derivative of the wave function, what we are going to get is the first derivative. So yeah, it's all right. Yes, I technically am doing the second step first, but that doesn't matter. So minus h square upon 2m. So I know this to be psi dash of x from minus epsilon to epsilon, and minus, we know this is, since 0 is contained in here, this is minus v naught psi of 0 is equal to e times, now this integral here. How do we go about solving this? Well, I'll just leave this integral as it is for now. Psi of x dx. Now, what we can do is we can consider the limit where epsilon tends to 0. So, essentially, okay, here I should write what I'm doing. Integrating both sides. One more new entity. Yes. So, integrating there should be no text boxes here. So, yes. integrating LHS and RHS. So if I take the limit epsilon tending to 0, then I shouldn't have written this as psi naught. Apologies. This will be psi of 0, like psi at 0. Okay. So if I were to take limit taking limit epsilon tending to 0, what we will have is as epsilon tends to 0, this integral will actually tend to 0 because my limits of integration are coming closer and closer and closer. So whatever the integral of psi of x be, if the limit, like the initial and the final point of my integral become the same, then the integral will vanish. So essentially what we will be left with is this minus h squared upon 2m. However, this is not an integral. Like this is already a difference of 2 points. Now we will see what that is. So this is essentially psi prime at 0 plus minus psi prime is the first derivative, 0 minus. So I will write this here. Psi prime is equivalent to d psi upon dx. Okay, yes. And this quantity has already been integrated, that it has no more epsilon dependence. So making epsilon tend to 0 will have no bearing on this quantity. So minus V naught psi of 0 is equal to 0. So what this tells me is, well, in a second. So let me just move everything to the right, so which implies psi prime 0 plus minus psi prime 0 minus is equal to minus, so this will go to this side, the minus will become a plus, and then this minus will go there, 2m v naught upon h bar squared psi of 0. Now what does this mean? What this means is the value of the derivative of the wave function as I'm moving. So 0 plus implies 0 plus and 0 minus are neighborhoods, again, like basic analysis or introductory calculus courses. Neighborhoods okay, fine. To the right to let me write this in a better way. So what are 0 plus and 0 minus? Plus, 0 minus points in the vicinity of 0, like very close to 0, respectively to the right and left. So 0 plus is points to the right on the positive side of the real line, and 0 minus are to the negative side. Right. Okay. So what this is telling is, as I'm crossing 0, the value of the derivative is actually changing. So what this implies is, what this statement explicitly implies is, the derivative of the wave function is no longer continuous. So if you remember last week when I was talking about the different properties of the wave function, when it came to the derivative of the wave function, I said it is a condition that is frequently dropped. So this is one example where we can explicitly see that for this equation to have a meaningful solution, this condition has to hold. However, we have not come any closer to solving this solving the Schrodinger equation for this potential. But as you are going to see, the actual solution is not that complicated. So now how do we solve this? Now remember, this problem also has three regions. So region 1, region 3, or rather let me say this is region 2. Apologies. And region 2 is only around 0. Like region 2 is like almost exactly that one point at 0. Okay, so this is region 3, just 0. And the Dirac delta function is 0 everywhere else. So the potential is 0 in regions 1 and 2. And we are looking for bound states. So what does bound state mean? Again, this was discussed yesterday. Bound states are states that have an effective negative energy, which implies E, like essentially bound state is a state where E is less than the potential. In this case, the potential is 0. Therefore, this will automatically imply E itself is less than 0. That is the only condition that I'm caring about. So how do we solve this? Then I know in regions 1 and 2, I know minus h squared by 2m psi double prime of x is equal to E psi, where I know E is negative. So this would imply E psi of x. Psi of x is equal to, or rather, sorry. Oh no. Psi double prime of x is equal to minus 2me upon h bar squared psi of x. Now this quantity entirely is negative. This quantity is negative. So this implies I will have psi of x is equal to a e to the power alpha x plus b e to the power minus alpha x, where alpha is equal to minus 2me upon h bar squared whole power half. I hope this is clear to everyone. Like this is exactly what we did last week. And now we have to impose the condition that psi of x should be finite. That is not a condition we can violate. So if it is finite, then in region 1, which is for negative x values, I will have, so in region 1, the solution will imply a is equal to, a not equal to 0 and b is equal to 0. And in region 2, a equal to 0 and b not equal to 0. Now what are the values of a and b? How do I find that out? The answer is actually very simple. Psi of x is continuous. So the derivative of psi is not continuous, but psi of x itself is continuous. So psi of x has to be continuous at x equal to 0. So continuity, so essentially what happens is, yes, let me go back to the figure. So over here, we have now been told that in this point, psi of x is a e to the power alpha x, oh no, a e to the power alpha x, and over here, we have been told that psi of x is b e to the power minus alpha x, minus alpha x. Now, as x tends to 0, this function will tend to b. As x tends to 0, this function will tend to a. And at x equal to 0, both of these values need to match. The function left limit and the right limit should converge. So that is essentially what I'm writing here. Continuity at x equal to 0 implies a is equal to b. That finally implies psi of x is equal to a e to the power. If a is equal to b, I can just replace that. And we also know from what we worked out in last week that this solution can be written as minus alpha mod x. Like the minus and plus, the sign flip can be combined and written as e to the power minus alpha mod x. So when x is negative, mod x will give me a positive value, and this will be a negative value, and it will vanish to 0 as x tends to infinity. And for positive values, of course, it will be x and again vanish to infinity as x tends to plus infinity. So the wave function is finite everywhere. It is also continuous. Now, how do I find the value of a? For that, we can use this equation right here. Now, from this, I know psi of 0 is equal to a, because it will be e to the power minus alpha times 0, which is 1. And additionally, d by dx of psi, essentially psi dash of x, is going to be a e to the power. So there are two possible cases. I will need to consider the case where x is negative and x is positive. So when x is negative, yeah, so let me write it like this. Let me say at 0 plus. For positive values of x, the wave function will take the form a e to the power alpha x. So taking the derivative of that will give me a times alpha e to the power alpha x. Oh, sorry, a to the power minus alpha x. Sorry. Because mod x will be x and there will be a minus sign. So this is going to be minus alpha, yes. Minus a alpha times e to the power, yes. And in 0 plus, I will need to make x tend to 0 here. So this is going to be minus a alpha. And similarly, if I were to work out d by dx psi of x 0 minus, that will be, there will be no negative sign in the exponent. So we will have a alpha x. Oh, wait. That better. Yeah. And at 0 minus, and this is again going to be a alpha. So from this we can see that, so substituting these two values in this relation, we will get so let me call this equation 1. So substituting in equation 1. we will have minus A alpha is equal to minus 2m upon h bar squared, oh, v naught h bar squared times A. Is this correct? Yep, yeah, this is correct. So this will give me, like I can, so this is going to be minus 2 alpha A is equal to, wait, am I doing this correctly? Is this equation correct? This is at psi of 0. So, aha, I'm sorry. There was one step that I missed. I would have appreciated if someone had pointed that out. Does not matter. So the value to A can actually be found by considering renormalization. I should have integrated mod psi squared from minus infinity to infinity to find the value of A. And that needed to be substituted here in order to get the answer in terms of uh, V naught. So what I shall do is, I will just write the remaining steps because this problem was there just to like emphasize the concept. So what I will do is I will just write everything else as comments here so that we can move on to the actual syllabus of today because we've spent almost half an hour on this. Yeah, so let me just write it here. Use renormalization condition to find A and then substitute in equation 1 to solve the problem. And I can actually get rid of this. Yeah. Now I can also do one more thing. Just select this, all of this over here. Can I? No. Resizing will cause overlaps. Yes. Okay. So this is how you solve this problem. In fact, now there is a reason why I solved this problem. That was to introduce you to the properties of the Dirac delta function, which, as I said, will be appearing frequently in the later portions of the course. Incidentally, I could have established that the derivative of the wave function need not be continuous using the particle in a box itself. So let me quickly do that. So if I consider particle in a 1D box, so V of x is given by 0 if x belongs to 0 comma a and infinite otherwise. Now for this we know psi of x is equal to square root of 2 by a sine n pi upon a times x for x belonging to 0 to a, and again this is a piecewise definition. 0 otherwise. Now if we look at the derivative of the wave function to the left and right of 0, this is going to be a constant times the cosine function, which at x equal to 0 will go to 1, which implies psi dash of x at 0 plus is not equal to 0. Whereas the wave function is 0 everywhere on the negative x-axis, which implies psi dash of x at 0 minus is always equal to 0. This implies derivative of the wave function is discontinuous. Is discontinuous. In fact, there is a general rule which I am writing here without proof. Whenever the potential is discontinuous, then the derivative then the derivative of the wave function is also discontinuous. Is also discontinuous. Once again, I track this all the way up. So discontinuous. So this is the last takeaway point that I wanted to discuss from week 1. Please remember this. Do not always assume that the derivative of the wave function will be continuous. It will be so if and only if the potential itself is continuous. The proof for that is very similar to what we did here. Just integrate on both sides. If it were a continuous function, this integral would also have vanished. So then on the left hand side I will have the difference between the derivatives. The right hand side I will have 0. So the difference between the derivatives is 0, which implies the derivatives themselves are continuous. When V naught is not continuous, that discontinuity will be absorbed into the first derivative of the wave function also. The wave function itself will be continuous, as to be continuous. Okay? Yes. So now let me just take a sip of water. Yeah, thank you very much. And yeah, what was he saying? Yes. So now we come to the first topic of the day. We are looking at the Kronig-Penney model, which is a toy model that represents a one-dimensional solid. In reality, yes, we can create 1D structures, but to call them a solid would be a stretch. And especially solids that are being considered on this scale are very difficult to manufacture, and they do not exist in an isolated space. The best we can do is to grow it on top of a 2D or a 3D structure. So a pure 1D structure very rarely, if at all, like exists in nature. However, this time model will allow us to understand many of the uh, like salient features of periodic systems. So first, what is the potential in the Kronig-Penney model? The potential is of this form. V of x is equal to some V naught for x belonging to 0 to a and 0 for x belonging to A to B. I think I will close this part. A, and I will say A to B, and with another condition, V of x is equal to V of x plus L, where L is given to be A plus B. So how does such a potential look like? Such a potential looks like, yes, now I will do the sensible thing and draw a thin axis. And potential profile is going to look something like this. Then it is going to be 0. Once again, over here it will continue rising, and then again it will drop to 0, and then it will go on again. And then rise up again. Yes. So likewise going this way, and periodically extending in both these things, and this region is the fundamental period. Essentially, this region right here is what I shall call the fundamental period, and this thing has length L, and this is x equal to 0, A, and A plus B. Oh, no, I should have written A plus B here. I'm sorry. One small correction here. So I will write this as A to A plus B. Essentially starting from A and moving a distance of B. Okay, so the complete L is from 0 to A plus B, which is A plus B. Okay, so yeah, that. Now, first question is this. So we will look at the properties of the aspects of this by solving the following problem. So first, we need to derive not first, that is the only thing we have to do in this problem. We need to derive the boundary conditions for the wave function corresponding to the above periodic potential. Yes. So how do we do that? So let me just draw a closer snapshot where I will only care about the fundamental period. Okay, then we have V naught over here. Let me also write that. V naught over here. And the axes need to be labeled. So X and V of x. Yes. So again, V naught. Yes. Yeah. So we have the potential coming from here. We shall not consider this. We stop starting from 0 to A to L. Now the regions of interest for us are the following. This is region 1, this is region 2, and technically region 3 and 4 are also required, but right now we will stick to region 1 and 2. Now first question, what kind of solutions are we looking for here? Yeah, again I should have mentioned that over here. So boundary condition for bound state wave functions. So can someone tell me what the bound state condition for this problem is? Anyone? Any suggestions? What energy values E will correspond to a bound state in this potential? Should E be greater than V naught or should it be less than V naught? Okay, so this has already been discussed, so I will recommend that you go back and look at the previous week's notes. Bound state automatically implies E is less than V naught. Okay, so we are looking at solutions where E is less than V naught, and of course, if E is less than V naught, it will still be greater than 0. So the general solution in region 1, I'm not going to solve the whole thing. We already have solved this before. Psi of x is going to be a e to the power alpha x plus b e to the power minus alpha x, where alpha is equal to 2m v naught minus e upon h power squared whole power half. Yeah, so this is alpha. And then we have into, so here psi of x is going to be, you know what, for simplicity, I'm going to lose the exponential notation. I'm just going to write c cos kx plus d sine kx. So these are the solutions here. So first things first, boundary condition number 1 is psi of x is continuous at x equal to a. So that is the first. Okay, even before going into that, um, so how many boundary conditions do I need to solve this problem? Can anyone make an estimate? How many unknown quantities are there in this equation? Like, feel free to say anything, like it's all right even if your answers are not correct. What are the quantities that we do not know in this equation? So the unknowns, like if you look at this, can be A, alpha, B, C, K, and D. There are a total of 6 unknowns. However, oh yeah, I forgot to write what K is here. K is equal to 2me upon h bar squared whole bar half, the square root of this quantity. However, we know that alpha depends on E. So there are 5 unknown quantities, A, B, C, and D, and E. So we will need 5 equations to solve for these 5 unknowns. So this is the first set of equations. First equation, which is, so at x equal to a, so that will tell me, let me write the equations in red. A e to the power alpha times a plus b e to the power minus alpha times a is equal to c cos ka plus d sin ka. So this is the first condition, that these two have to be continuous. Now what about the derivatives of the wave function? Any guesses? Any guesses? So this is another peculiar situation. So essentially what's happening is, even though this is a discontinuous potential, there will be like the continuity of psi, the derivative psi dash is still applicable here. The reason for that is, even though v looks, I mean v is of course discontinuous, because if I'm approaching a from the right side, v of x is 0. If I'm approaching a from the left, v of x is v naught. However, it is constant on both ends. Its derivative is well defined, and in fact its derivative is also 0. So for such special conditions, it is required to take the uh, continuity of the derivatives also. So that will give us the second equation, which is psi of x, psi dash of x is continuous OUS at x equal to a. So that will lead to the equation a alpha e to the power alpha a minus b alpha e to the power minus alpha a, which is further equal to c minus c sin ka plus d cos k. So this is equation 2. Remember, we need 5 equations because there are 5 unknowns here. Let me put up a new slide. Now the other point of interest in this is at x equal to L, or x equal to a plus b. The wave function once again needs to be continuous across these 2 points. But do I know the solution here? Like, is it possible for me to know the solution here? The answer is yes. So what do I use to find the form of the wave function in this place? Is there any rule that allows me to find that? Any responses? Nothing? So essentially, to find the value of the wave function in region 3, I shall be using Bloch's theorem. So in 3, I know psi of x plus L is e to the power I k L times psi of x. And if you notice, region 3 is the same as region 1, only moved forward by a distance L. So that is exactly what we shall be using. So in region 3, therefore, psi of x is equal to e to the power I k l times a e to the power. Now remember, x plus l takes me back to x, which implies whatever. So if I take this point to be x plus l, then I need to evaluate the function at psi of x. I need to evaluate back at, so if I'm considering the evaluation of the point here, then Bloch's theorem tells me that I need to move all the way back to this point by, wait, is this length L? Oh yeah, of course this is, yes. All the way back here to a distance L to evaluate the function. So how do I write that over here? I will write it as e to the power alpha times x minus n. I hope that is clear. Plus b e to the power minus alpha x minus n. And we are looking at continuity at x equal to L. So that is the point at which we are verifying the continuity of these equations. Okay, so equation. So this, yes, I should have written this in red. So, so psi of x plus m is equal to e to the power I k l psi of x. This is the Bloch's theorem. Bloch's theorem. And this is equation 3. So now coming to 4, I will need continuity of psi of psi at x equal to L. So now this is going to be, this is to the right hand side. So I will start with the left hand side, which is C cos KL plus D sin KL is equal to e to the power I k l times, I need to substitute L in all of these. Luckily for us, all of them will become 1. So we'll be left with A plus B. And similarly, we will also need to consider the derivative. So this is the fifth equation. Continuity of psi at psi prime at x equal to L. This should have been in red. I think I know how to do that. Yes. So the final equation is continuity of psi dash. So that is going to give, oh my god, oops, sorry, fumbled. I forgot to write the k's here. CK and DK. Yeah. So now this is going to be Ck minus Ck sin Kl plus dk cos Kl is equal to e to the power I Kl is a constant, so nothing happens to it. On the inside, we can quickly look at this and find that an alpha will come here and a minus alpha will come here. So now, and otherwise everything else is going to vanish, and not vanish, it's going to become 1. So we are going to have A alpha minus B alpha. A similar condition would have applied if I considered the uh, value of the wave function starting from this side. However, to take it from this side, I need to do some different translations, and the sine and cosine values may not be the best choice to consider here, which is why I took the regions 1, 2, 3 as shown over here. Okay, so these are the 5 equations. So these are the 5 equations that one needs to solve the Schrodinger equation for this potential. So this is what you would have seen in the class as well. Okay, so now if we can take all of these 5 equations and consider the case where they have valid solutions, essentially the determinant representing these equations should be set to 0. So if we go through all of those things looking for a unique solution, we will end up with an equation that looks like this after rearranging certain parameters and making certain approximations. So these boundary conditions are where we get the idea of electronic bands in solids. So now let us see how that happens. So this equation, you need not know the derivation of this equation, but know the rough idea of what terms are present. See, you're going to have a sine term and a sine hyperbolic term, which is essentially corresponding to the e to the power alpha, e to the power minus alpha terms. And then you have cos, like the trigonometric cosine, and the uh, hyperbolic cosine. And that should be equal to cos of k times L. So this is the equation that we may derive starting from these initial boundary conditions. So now what we can also do here is we can observe that k depends only on E. Okay, so this is, let me write here, k is defined as f of E, and alpha naught is equal to f of E and V naught. So alpha depends on the potential value also. And of course, I know E should be below V naught for bounded solutions. So what we can do is we can eventually plot this function. So what we do is we consider, like, this variable xi is the normalized energy quantity. So xi is equal to, I can write it here. So xi is equal to E by V naught. So it's the normalized energy. And whereas K, no wait, yeah, I got it. K does not depend on xi. K only has E dependence. Okay, so this curve here, the black curve here, this is f of xi. So this is f of xi. Now I know the right hand side of that has to be cos k plus b, and we know this is minus 1 greater than or equal to cos greater than or equal to plus 1. So it is strictly bounded between plus 1 and minus 1. So we draw lines from plus 1 and minus 1, and we see where all it intersects this particular curve f of xi. Only the points that lie in this region have a valid solution for all these boundary conditions. For all other energy values, we do not have valid solutions for the above considered boundary functions. So this is essentially the formation of energy bands. So this is how the structure will look. If we look at a realistic solid, so this is from the Kronig-Penney model, this is a toy model. Now, if we look at a realistic system, then the atomic potentials are going to be like this. So this is the 1 by r squared, sorry, the 1 by, oh my god, why am I getting stuck here? Yes, the 1 by r scalar, 1 by mod r scalar potential. So depending, which it only depends on the distance between the electron nucleus and the atom. So, and these bigger slopes here represent that the crystal is kind of bounded. So for any finite crystal, we shall have a potential of this form. And what we can observe here is this set of values of xi. So xi is E by V naught. So this is essentially the allowed values of energy. So this is the first set of allowed values of energy. Then we have a forbidden gap starting from here to here. So let me say this right here is the first forbidden gap. Okay, so and then I will have another set of allowed energy values and another gap. Then there will be another set of allowed values and then another gap and so on and so forth. Two things we can notice. First, number of allowed states increases with each band. Yeah, is huh? No, I'm sorry. With each successive band, yeah, that's the thing that I'm supposed to write. Not with each band, each successive band. So essentially, what I mean here is, if I consider the number of allowed energy levels in the first band and the second band, the number of allowed energy levels in the second band is going to be higher. The allowed between the second band and the third band, allowed number of energy levels is going to increase further. Essentially, the spread of the energy values is going to be higher. And additionally, the gap between successive energy bands reduces. So these are two properties that are observed even in conventional 3D solids. Like these are facts that are experimentally verified. So these are the two important takeaways from this. Like you don't need to remember this equation in full, but at least remember how to derive that equation, and these properties should be always remembered. So there are like several forbidden gaps here. Essentially, every successive forbidden gap keeps becoming smaller and smaller and smaller. And the number of allowed states keeps increasing as we move from one band to the next. Okay, so this is the transcendental equation and the allowed energy values. Then we can plot, remember, k is a function of E. So I can plot the EK relation. So that will give me a curve like this. So this is called the dispersion relation. Which is the EK relation. Okay, so this tells me the dependence of E on K. Now, for a free particle, yeah, let me do that in the next slide. Drag this down. For a free particle, we know E is equal to h squared k squared upon 2m. So this is the quantity that we know. This implies this is the K relation. So E is proportional to k squared. And that is what is represented by this parabola. So this free particle corresponds to E is equal to h cross square k squared upon, did I write it as h square? No, h cross square k squared upon 2m. What we observe in the Kronig-Penney model is the energy is not, the EK relation is not that straightforward. It does follow a parabolic trend, but we have the first allowed set of energies, and then we have the second allowed set of energies, but they will correspond to two different pi values. Essentially, this is the cosine function. So it goes from 1 to -1. So in that region, the value of theta will vary from minus pi to not, yes, the argument of the cosine function will vary from minus pi to pi. In the second region, it is going to vary from, so this region, let me use a different color here. This region has minus pi to pi, whereas this region here is going to be minus 2 pi to minus pi, and then pi to plus 2 pi. So essentially, each of these correspond to a segment of 2 pi angles. So minus pi to pi is 2 pi, minus 2 pi to minus pi is pi, and pi to 2 pi is pi. So this is one segment corresponding to pi by L technically, pi angles. This is corresponding to pi angles, and similarly, the lines will stretch. In truth, as we go higher and higher and higher, this curve will indeed start representing a parabola, and these gaps will slowly, yeah, I blinded myself. The gaps will slowly start reducing. So higher, the higher level bands, higher the level of bands we move to, the more free the electron will tend to behave. So yeah, yes, yes. The higher the, the more free the electrons will tend to behave. Additionally, there is this notion of writing the whole representation in the reduced band structure, where we kind of move this curve over here and this curve over here, and this would have been explained in class. If you have any questions, feel free to ask. Otherwise, we'll proceed as such. So this is the dispersion relation directly. So this is the dispersion relation that we have. Okay, so there is one last concept we will look at today before ending today's session, and that is that of effective mass. Now, over here, I wrote E is proportional to k square. The proportionality constant depends only on the mass of the particle. H bar square is a universal constant, so it is going to stay for everything. So I will write this here. The proportionality constant or rather, let me not write the proportionality constant. So this implies, let me write it like this, d by dk is equal to, so 2 h cross square k by 2m. So Yeah, the 2 and 2 will cancel each other out. And further, d squared e upon dk squared will be, the k dependence will also go. So we will be left with by m. This implies m is equal to h bar squared divided by d squared e upon d k squared. So this is true for a free particle. This is true for a free particle. Like I have not done any special derivation here for the general case. In general, the point is this. The second derivative of the EK diagram is a good measure for the inverse of the particle mass. So what does this mean? Now, if I were considering this parabola with dotted lines, so this free particle corresponds to mass equal to m. Now, because of this, I know these other curves cannot correspond to a parabola with mass equal to m. Each of these parabola, and since they are not even parabola, each of these segments, curved segments, in fact, they have their own relation as I move from one band to another. And that will have its own mass. So that brings us to the idea of effective mass, where effective mass will be defined as follows. So what is effective mass? So effective mass is used to describe the particles in an interacting medium. So essentially when an electron is present in a medium where it is interacting with other objects, I can either choose to keep track of all these interactions and do the calculations over and over and over again, or what I can do is I can average over all of them and write it as the electron now behaves as another charged particle with a new effective mass which is free. Like by averaging over all the interactions, we kind of get rid of them, and the effective mass tells us the same system, that is the electron interacting in a solid, will be equivalent to a particle with the effective mass of the electron that is completely free. And in solids, the effective mass is the inverse of the curvature of the energy bands. So what is the curvature? The curvature C is equal to, how do I write this? We can write it as, uh, yes, 1 plus, or rather, let me say, let me write it like this. So if I have y equal to f of x, then the curvature of y is equal to 1 plus df by dx, or I should write dy by dx, dx 1 plus dy upon dx, the whole square divided by d squared y upon dx squared. So this is the general formula of the curvature. Now typically there is a very important reason why we will not consider the, why we will consider the effective mass only at certain chosen points. The answer for that is actually quite straightforward. We will always only consider the effective mass at this point or this point. In the reduced zone, either over here or over here or over here, or over here, or over here, or here, or here. Essentially, effective mass is relevant only at the band edges. The reason for that is at the band edge, depending on whether it is a minima or a maxima, the second derivative is going to be either positive or negative, respectively. If the derivative is changing sign, then that implies at some point the derivative will have to have a zero crossing, the second derivative. Like second derivative is positive here, it is negative here, which implies somewhere in the middle it will reach a zero value. Let us say at this point the second derivative reaches a zero value. That at that point I will know that the curvature goes to infinity and the inverse of the curvature will give me zero. So wait, oh God. Yeah, I made a mistake. So this is not the curvature, this is the inverse of the curvature. So yeah, you cannot have zero effective mass. I apologize. So the point where d square y by dy square is zero, so I will write this here. So d square e upon dk squared equal to zero implies infinite effective mass. And similarly, if d square e by dk square is negative, then we will have negative effective mass. So what does this mean? What does a negative effective mass mean? So to understand this, we can think of a very simplistic example. Let us say I have a bottle of soda or some kind of a like aerated drink, a kind of a liquid which has bubbles of air in it. Now, if those bubbles are free to move, we know those bubbles will move upwards towards the surface of the liquid. Now that is due to a density difference. Like we understand how that happens. However, I can simplistically model these bubbles moving in the liquid as an object of negative mass moving in gravity. So that bubble which has air inside of it, of course the air molecules have positive mass. I'm not saying the air molecules have negative mass, but when inserted into water, when it or some liquid, when interacting with some liquid which is more denser than the air, then I can effectively treat it as a system with negative effective mass. And so gravity for positive mass objects will usually pull it down, and in this case, since they have a negative effective mass, I will say that they will move up. And that is essentially the idea of defining negative effective mass. So the sign of the effective mass dictates the motion response. So if it has a positive effective mass, it will move with the force. If it has a negative effective mass, it will move against the force. Like if I'm pushing a negative effective mass particle from left to right, it will actually move from right to left. Okay. So yeah. So negative effective mass is analogous to bubbles in water. Okay, so with that, we come to the final problem for today. So we have a dispersion relation that is given as such. So we have h square upon 2n divided into cosine of 8k naught plus delta k. So let us try to find out the minimum and maximum energy first. So for that, first we will have to look at dE upon dk is equal to 0. So that is going to give us 8 is the multiplicative factor. So Yeah, so I should have written this as not delta K but K. Yes. K naught plus K. Yes. Now it is correct. So this K naught is a constant shift. So this is always there. In fact, I could have written it as K plus K naught. So now when I do the derivative, I will be differentiating with respect to K. K naught plus K is equivalent to K. There will be a multiplicative factor of 8 coming out. So we have h bar squared upon 2m and times 8 into, of course, there is going to be a negative sign. Derivative of cos is minus sign, so that is sine of 8 k naught plus k. So yes, now depending on where k naught is, sorry, apologies. So oops. Or no, having a non-zero value of k naught is kind of okay for this problem. So essentially for this quantity to be 0, I know k naught plus k should be equal to n times pi. Yes, where n is equal to, here n equal to 0 is allowed. So 0, comma 1, comma 2, 3, and so on and so forth. So essentially the nearest minimum that we can think of is k equal to minus k naught. Not minimum, the nearest minimum or maximum. Now let us see what the value of what kind of a point it is going to be. So I know k equal to minus k naught is either minima or maxima. Oops. Or maximum. Okay, so yeah. So to find out if it is a minima or a maxima, I need to take the second derivative. So that is going to be d squared e upon dk squared, which will come out to be, the minus sign will stay, minus h squared upon 2m. Another factor of 8 will come out, and we will return back to the cosine function again. Cos 8 k plus k naught. Now we know that if k is equal to minus k naught, the inner argument becomes 0, which implies the cosine value will be plus 1. Therefore, d squared e upon dk squared is less than 0 at k equals minus k naught, which implies minus k naught is a k equal to minus k naught. It's a maximum energy point. So, okay, now I know d square e upon dk squared is negative, and we also know the value of it. So, what is the value of the second derivative? It is going to be 64, oh, not 64 square. It's going to be minus 64 h bar squared upon 2m. Now, I know the effective mass m star is the inverse of the curvature. Now, but at an extremal point, dy by dx is going to be 0. So, at an extremal point, the curvature is just going to be, inverse of the curvature is just going to be d square 1 by d square y by dx squared. So m star in this case is going to be h bar squared upon d2e upon dk squared. So this is going to be h bar squared divided by 64 h bar squared by 2m, which is equal to 2m by 64, which will give me m by 32. So at the maximum energy point, this particle will behave like a free particle which has 1 by 32 mass of the original particle that I am considering. Similarly, we can consider the case where the energy is at the minimum. So for that we need to consider k is equal to k plus k naught equal to pi. So that will give us k is equal to pi minus k naught. So all the analysis will continue. I will get the same mass with a negative value. So similarly, it can be shown that k equal to pi minus k naught is a point of minimum energy and the effective mass at that point is, oh wait, I forgot the negative sign. Yeah. So before I finish this sentence, at the maximum energy point, the effective mass is always going to be negative, which implies if I try to push the electron in one direction, it will always end up moving in another direction. Now, how and why this is happening, I will maybe describe, not maybe, I will describe in the next session when we are talking about density of states and occupancy and those things. Because once we look at the state picture and the actual energy occupancy and, sorry, electron occupancy of those states, the arguments that I shall present will make more sense. Right now, I will not go into that detail. We just need to get the basics introduced. So at a maximum energy point, the effective mass is going to be negative, and at the minimum energy point is m by 32, which is the positive value, which is positive. So coming back to this diagram for just 1 second for the final remark. So if we look at this band structure, so I can also identify those points here, but it will be much more easy to identify it here. So this band has like maxima at the edges, minima at the center. This band has a minima at the center, sorry, maxima at the center, minima at the edges. So at the center of this band, there is going to be negative effective mass. At the edges, there is going to be positive. Here, at the edges, it is going to be negative. At the center, it is going to be positive. Every odd number band will have positive effective mass at the center in the Kronig-Penney model. Every even band will have negative effective mass at the center and positive effective mass at the edges. So now, how does this make a metal or a non-metal or an semiconductor or an insulator? This is discussed in your lectures. However, I don't want to bring that directly into today's discussion. Along with the discussion on the effective mass, I shall also invoke this concept in the next problem solving session. So I think we have done enough for today. So what I shall do is, just 1 second, check. Yeah. So what I shall do is stop today's session with this. In fact, we can have a proper discussion for the density of states also in the next session, because like I'm telling this because I know your assignments. Whatever assignment questions that exist for the density of states, just go through what is given in the last lecture slides, and that should be more than enough to guide you through that one or two problems. A more detailed discussion, I will essentially start from the idea of effective mass in the next session, and then jump into density of states, and then we can, move on to successive topics like that. So with that, I will bring today's problem solving session to an end. And I thank you all for attending, and hope that this was beneficial to both the people who are currently attending the session and will watch the video eventually. We shall meet again the same time next week. So let me stop the recording.